course on Introduction to Statistical Mechanics, is to talk about two things which are Potts model and FK percolation. And okay, there are multiple reasons to do this. So first, it's a way to give an extension to what we have done for the Ising model, also to link the two parts of the course, because FK percolation, well, percolation, if you want, is a particular case of FK percolation. And also it will give an illustration of how the method we have, and even the results we have seen, well, it can be applied for other models. So, okay, so let me go back to the Ising model, and today we are going to only consider the case with zero magnetic field. So if you remember the Hamiltonian for the Ising model with free boundary condition, or with zero boundary condition, it was given by beta times the sum of the sigma x, sigma y. And a way you can rewrite it is beta times the number of edges in the box minus 2 beta times the sum over x, y in E lambda times the indicator that sigma x is different from sigma y. Okay, so basically what this means, because this is constant and does not depend on the spin configuration, is that if we define this thing to be h bar lambda beta sigma, the model which is defined with this Hamiltonian is the same model. Okay, because adding a constant to the Hamiltonian, it just changed the Gibbs weight and the partition function by the same factor. So when you look at the Gibbs distribution, you have exactly the same thing. Okay, so why am I saying all this? Well, because the idea of Potts model is just to look at, well, Ising model, but with more than two possibilities for spins. Okay? And if you have this expression here, it's not obvious. Here it makes much more sense. So, yeah, so what is Potts model? And like Ising model, Potts model was not actually invented by Potts. It was a model that was suggested to him by his PhD advisor. So when your advisor gives you a problem, maybe, I mean, the problem will bear your name later. Okay, we just defined a measure mu. Okay, I will just define, okay, this thing, I will just call it beta bar, okay, just to avoid having a 2 everywhere. And I will just define mu lambda beta sigma, which is equal to exponential minus beta bar times the sum over xy in E lambda indicator sigma x is different from sigma y. And now the important thing is that here we can make sense of this even for lambda omega, which is equal to, yes, just 1q to the lambda, where q, okay, is something larger than 2. Okay, so if q is equal to 2, it's just the Ising model. Okay, it's just that we have renamed the -1, 1. We have changed to say that it's 1, 2, but it doesn't change anything. If q is larger than 3, it's a Potts model, strictly speaking. Okay, so for q larger than 3, that's the q Potts model. Okay, and so here there is a first remark that we can make is that maybe a big part of what we have done to study Ising model doesn't work to study Potts model. And the reason is that, you see, the -1, 1, there was a natural order on the set. Okay, which was, okay, if you take -1, 1 to the lambda, or even 1, 2 to the lambda, there is a natural order on the set. Okay, just the coordinate-wise order. Okay, here you might tell me, oh, well, okay, here also there is a natural order. It's also the order by coordinate. But here the problem is that, I mean, you have an element, a set with q element, and all the q elements, they play symmetric roles. So of course, the natural order does not translate, I mean, does not fit this reality, and it will not help you at all. I mean, you have no chance to have things like FKG inequality to be true for Potts model if you just apply, well, for the order which is given by the coordinate order. Okay, just for this reason. Because when q is equal to 3, 1, 2, and 3, they have absolutely symmetric roles, so there is no reason to say that 1 is between the two others, okay, in terms of order. Okay, so I think the most popular approach to study Potts model is a representation of it which is called FK percolation. And, well, it's a percolation model which, okay, we will see is kind of strongly related to Potts model in the sense that, well, you can sample the Potts model by first sampling a configuration for the FK percolation and then doing some extra operation. Okay, so so let's consider now omega lambda, which is 0, 1 to the E lambda. Okay, we are looking at the percolation model. So configuration will be on the edges of my box. And I denote omega E in E lambda as a configuration in omega lambda. So it's a bit different from standard percolation. What we lambda PQ of omega, which is, okay, so first I will take P times O of omega, 1 minus P times C of omega, and then I will take Q times K of omega. So I guess O and C, you might guess what this should be. So O is simply the number of open edges. Okay, and the thing that I'm not sure, actually, I mean, I'm sure that these things don't sum to 1, so you have to divide by a partition function, which is just z lambda pq. It's just the sum over omega in omega lambda of p to the o omega 1 minus p. So the c omega k to q to the k omega. Okay, so what is O omega? It is the number of open edges in omega. Okay? I mean, we have a finite set of edges, so this O is something which is well defined. C omega, it's equal to the number of closed edges in omega, and it's just E lambda minus O omega. And K omega it is the number of connected components in the graph lambda E omega. Okay, where E omega, it's just a set of open edges. Okay, so if Q equal to 1, what we have is ordinary percolation. Okay. If Q is smaller than 1, okay, and this is something we are not going to talk about very much, but what you have is something that penalizes the graph with lots of connected components. And if Q is larger than 1, it's the contrary. It favorizes. And, okay. So why are we introducing this model? I mean, what's the connection with Potts model? So the thing is that if you sample a configuration according to this measure, basically you can get Potts model doing something very simple afterwards. So if you sample an edge configuration here, I mean, you get a random graph on the set of vertices okay, on lambda. And then what you can do is, for each connected component of this graph, you can sample uniformly at random and independently for each component a color, okay, between 1 and Q. Okay, I will call these things color. And then what you obtain in the end is something that has distribution, this. Okay, so of course, you have parameters here. So here, Q should be the same as Q here, okay? And here, 1 minus P should be exponential minus 2 beta, I think. We'll check that together now. Okay, so. Okay, so how to sample Potts model. Okay, and remember that we are in the free boundary condition case. Okay, I mean, here I'm considering that there is no interaction with the boundary, but like for the Ising model, for the Potts model, you could also consider that, say, you have edges linking lambda to the boundary, you take them into account, and everything outside of your box is either, well, it can be given by a fixed configuration, but maybe the most interesting cases first are the cases where what's outside the box is monochromatic, so say all equals to 1. Okay, so right now we are focusing on the free boundary case. And how do we sample Potts model? Well, first, we sample omega according to p lambda p q for each connected component of lambda e omega. We choose a color at random. Uniformly and independently for each component. Okay, so how can we check that this indeed gives you Potts model? Well, what I can do is, I mean, if you do this, then you have really two things. You have a spin configuration and you have omega. And what we can first do is write the joint law of the two things. Okay, so if you want to know, so you define this, which is a law of on this set. And the probability of observing a given edge configuration and a given spin configuration, well, first it's given by 1 over z lambda p q p to the O of omega 1 minus p to the c of omega and q to the k of omega. And then I have to multiply this by the probability of observing sigma given the fact that I have already observed omega. And, well, so, yes. What should sigma satisfy? So the first thing is that sigma should be monochromatic on every connected component of this graph. So in part, I mean, this is the same thing as saying that all the edges of omega, they are monochromatic. Okay, so first thing we have to put is the indicator that for all E in E lambda, well, for all xy in E lambda, sigma x is equal to sigma y. Okay, and then you just choose uniformly amongst the configuration that satisfies this. Okay, this is what the second step is. And the number of possible configurations you have, well, you have exactly Q choice per connected component. So you just take one at random amongst all of them. Okay, so here we have a simplification, and this gives you the expression for Q. Okay, so now if you, we want to look at just the distribution of sigma. So really what we are interested in is the sum over omega in omega lambda of Q lambda P Q of omega sigma. Okay, so let us try to see what that is. So, well, you have this thing, but this thing is not really important. It's just a constant. What we want to see is that what we get after summing is just something which is proportional to the exponential of our Potts Hamiltonian. Okay, so I have the sum over omega in omega lambda, p to the O omega, 1 minus p to the C omega. And okay, here maybe I should rewrite this thing here. I mean, this is kind of a condition on the, okay, this is not on E lambda, this is E omega. Okay, so, I mean, somehow this is a condition on the spin given omega. Maybe I should try to rewrite this as a condition on omega given the spin. And this is exactly the same thing as saying that if two spins on an edge are different, then the edge must be closed. Okay? Saying that every open edge is monochromatic, it's the same thing as saying that every non-monochromatic, every bichromatic edge is closed. Okay, so here I am for all x, y in E lambda, omega E. Sigma x different from sigma y implies omega E equals 0. Okay, so, I mean, basically, if I didn't have this condition, this sum here would be equal to 0. This sum here would be equal to 1. Okay, because I'm just summing p and 1 minus p for every edge. Okay, now, here I'm not summing over every configuration. And in fact, for edges that are not monochromatic, I don't have the p term. I just get 1 minus p. So this sum here okay, I can rewrite. It's just the product over the E bichromatic E of 1 minus p times the product over monochromatic E of p plus 1 minus p. Okay, this is what you obtain when you factorize the product. And so this is just 1 minus p times the number of bichromatic edges. Okay, which is something you can rewrite as exponential minus log 1 over 1 minus p times the sum over x, y, in e lambda. Indicator sigma x is different from sigma y. Okay, so basically you should have beta bar, which is equal to log 1 over 1 minus p. Okay, which is p is equal to 1 minus exponential minus beta bar. Okay, remember that this beta bar is 2 beta for the Ising model. Okay, so not only, I mean, this weight we obtain is exactly the weight for the Potts model, so it means also that this partition function here, okay, as a byproduct, we obtain that this partition function here is exactly equal to this z lambda beta, okay. Yeah, I mean, this thing depends on Q, so. Okay, and if you think about it from this proof, you get something else, because you can do it both ways. What it tells you is also that you can sample use FK percolation using Potts model. So first you sample Potts model, and then you make percolation of parameter P on all the on the set of monochromatic edges. Okay, so I mean, like you look at Potts model, this kind of splits your graph into connected components of some colors, and on this connected component you do percolations with parameter P. Okay, so okay, so if you remember well, for Ising model, we are really interested in what happened in the limit when your box goes to infinity. So of course, this is the same question you would like to ask for Potts model, and in particular, you would like to say, okay, if I send the size of my box to infinity, do I have long-range connection between my spins? Okay, so in particular, if I fix a boundary condition, okay, and I make my spins interact with the boundary, do I still see the influence of the boundary at the origin after I send the boundary to infinity? Okay, so these questions about uniqueness of Gibbs states is still pretty much can be asked also for this model. So if you want to think about these questions, maybe you should try to see how to define an FK percolation that would correspond to the Potts model with some boundary condition. Okay, because our tool to investigate I mean, even in our definition of Gibbs states, okay, the notion of boundary condition was really important. So, okay, maybe before doing this, just a small remark is that, okay, here, I mean, this connection gives you clearly a motivation to study FK percolation for when Q is an integers, but it's also interesting, okay, to look at it when Q is not an integer, and let me give you an example of this. So, if you look at the limit when Q tends to 0 of this, basically what will happen is that, okay, because Q tends to 0, you will favorize configuration which has minimal number of connected components. Okay, so really in the limit when Q goes to 0, okay, everything will concentrate on configuration with only one connected component. Okay? And if after that you take the limit when P goes to 1, well, you will have to consider, it will give you, well, it will have to concentrate on the configurations which have maximal number of open edges. Okay, so this thing here is exactly the uniform measure on the set of spanning trees of lambda E lambda. Okay, so what's a spanning tree? Well, it's just a subgraph of a graph, okay, so obtained by taking a subset of the edges, okay, and keeping the same vertices, which is a tree. Okay, and okay, this is an interesting object for a variety of reasons, and it turned out that yeah, this measures the uniform. Well, this is called the uniform spanning tree. Okay, and in a sense, the uniform spanning tree is a special case of FK percolation. Okay, a bit degenerate in the sense that you have to take well the limit when the when the parameters goes to degenerate value, and you have to take this limit in a certain sense, in a certain order. Okay. Now, pretty much all I'm going to say now is going to apply only to the case where Q is larger than 1. Okay, so the idea is really to consider your edges configuration as edges configuration on ZD. Okay, so just a sec. Omega is equal to 0, 1 to the ED. But what we are doing is, like for the Ising model, we are just fixing the value of the edges outside of a box. So if you think about what we have done, In this case, it's pretty much that we have fixed the number, all the edges outside the box to be closed. Okay? And okay, then if you are considering all of ZD, the problem is that k omega, is infinite. But the idea is that, really the number of connected components outside the box, it's infinite, but it's always the same, okay? So that's the reason why you can define here k lambda omega as the number of connected components inside the box. Because what's outside the box, basically, okay, it's infinite, but morally, it simplifies between the numerator and the denominator. Okay. So this gives you the Potts model with free boundary condition. If you want the Potts model with some with some other boundary condition, what you have to consider is really that all the edges outside of the box are open. Okay, so we are considering now P lambda PQ1. Okay, the other, I would define it as P lambda PQ0. Okay, and 1 and 0, they are just really the boundary condition. It's equal to well, P O omega 1 minus P C omega and Q to the K1 omega, okay, where K1, okay, here omega belongs to omega lambda, of course, and K1 of omega, it's the number of connected components for the graph. Well, basically, the set of vertices is ZD, and the set of edges is, well, the edges in omega plus all the other edges, so plus ED minus E lambda. Okay, meaning that everything that touches the boundary, it's counted as one component. Okay, and now if you want to sample pods with boundary condition 1, okay, what you are doing is exactly the same thing as before, except that for the connected component that touches the boundary, you just don't choose it at random, you take it equal to 1. Okay, and if you do the same algorithm as before, you will get Potts model with a random boundary condition, which is just, well, it's a uniform color, but which is chosen at random. Okay. Okay, so now, so we have defined, okay, two measures. Okay, the first one, which I now write with the superscript. Okay, and yes, maybe if you reread this and you wonder, there is something a bit not exact in what I said, that actually I've not exactly taken the same convention for this and for the Ising model. So here, you see, for the Ising model, the boundary was the external boundary. Now the boundary is the internal boundary. Okay, so basically, So basically the fk, the p1 lambda n pq allows to sample pods with boundary condition on lambda n minus 1, okay, if lambda n is equal to minus n to the d. Okay, because here, I mean, I'm the fact, yes, you see. My graph is like this. This is my box, lambda n. All these things are also linked to the boundary by other edges. Okay, so these things, they will be in the giant component that is linked to infinity, okay? And they will have to have the color which is fixed. Okay, so if I sample fk on this box, like the free spins that I will be able to choose, they will be on some box inside. Okay, so I've defined two measures, and now I will really focus on the measure with this one external condition, but I could make the same reasoning with the other one. And what I may want to ask is, well, can I take the limit when lambda goes to ZD of this thing? Oh, and of course, if I ask the question, the answer must be yes. And the reason why the answer is yes is that basically everything we said for the Ising model applies to this case. Okay, so remember what we did for the Ising model when we wanted to define the limit of this. Okay, and okay, the limit of this, I will call it P1, PQ. Okay, so maybe let's not define it as a measure, but we can define it as a state. Okay, so what we want to make sure is that the expectation of local functions with respect to this converges to some limit for every local function. And what is a local function? A local function, I mean, we have function on set of edges, so a local function is a function whose values really depend on the state of finitely many edges, which we call the support. Okay, so what's true here? Okay, and the idea is to give you an overview, so I will go quite fast on this, but you can check that all the details work. So what you can say here is that if lambda is included in lambda prime, f local with support of f included in E lambda, then what you have is that the limit when lambda, no, what you have is that, and okay. f increasing, sorry, what you have is that the expectation of lambda p q f of omega, it is larger than okay, so if you take an increasing function, then the expectation decreases when the box increases. So something very similar to what we had for the Ising model. When I say increasing, I say really increasing with respect to the coordinate order on 0, 1 to the lambda. Okay, because the advantage of going back to percolation is that now we have a completely natural order on the set of configuration. Okay, so okay, if this is true, basically you can conclude that so what you have is that star implies star, just using the same thing as for the Ising model, okay? You know that basically let's call it omega A. So these things are a base of increasing functions. They are these functions, okay, indexed by A, included in ED finite. They form a base of local functions. This monotonicity here, it tells you that well, these expectations, they will converge when lambda goes to ZD, and that the limit really does not depend on the increasing sequence you're considering. And therefore, because you have shown things for a base, you have shown convergence for every local function. Okay, so now the question is, why is this thing true? And maybe you have the answer, I don't know. So what was the reason why this was true for Ising? So if you remember, okay? Para essa desigualdade, na verdade, estou usando um resultado, uma desigualdade mais geral que a gente provou para Ising. So what inequality was this? Here, it's kind of 50% chance now. But, so this is just FKG inequality, if you remember, because okay, no, this okay. Yeah, okay. There was okay. Now I understand what you're saying. So it's FKG inequality plus some observation, which was the Markov property. So yes, so the first thing is to observe that this thing, it's really the same thing as for all E in E. Okay. So yeah, so this is the important thing, that the probability in the smaller box, it's just the same thing as the probability in the larger box, but if you condition everything in between the box to be open. Okay, and this is really something you can check using the Gibbs weight. I mean, you just have to check that the term Q to the K matches. Okay, because I mean this thing about the P, I mean these are just okay. So somehow, I mean these things, it's the percolation terms. It's independent on each edge. So what you really have to check is the thing about the K, and well, okay, you can just check this by hand. Okay, I would say it's actually a bit easier than for Ising. And then you can use FKG. Okay, so this is an increasing event. So what you have is that, well, the expectation of an increasing function condition to an increasing event, this is larger than, well, the expectation, just the expectation of the function. Okay, because when you write conditional expectation, okay, you get the expectation of a product divided by the expectation of something. And, okay, so here, of course, you have to prove FKG. So, okay, why is FKG true? Well, if you remember, for FKG to be true, we had a criterion. So, for FKG to be true, okay, it is sufficient to check okay, and that okay, maybe I call it G, I don't know. G of omega plus G of omega prime, it is smaller than G of omega max omega prime plus G of omega min omega prime. Okay, for all omega prime in omega lambda. Okay, where G is well, it's just log of P lambda PQ 1. Okay, I mean, you want what you want to say is that if my probability is of the sort is of this sort, so if the probability of a configuration is proportional to exponential G omega, and if this is true, okay, then FKG is true. This is what we had proved before. Okay, if you remember, we had proved something even more general, but this was corollary 1. Okay, so okay, if I take the log of the probability of omega, I don't really have to worry about the partition function, okay, because I would have log of the partition function, 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 everything cancels. So the constants here are not important. So, okay, so here, I mean, this thing, I can just take it to, okay, this is this plus a constant. And here I can just take it to be, well, log P over 1 minus p times O of omega. Okay, this is to take into account both open and closed edges. Okay, I'm just saying that P O 1 minus P C, it's equal to P over 1 minus P O times 1 minus P C plus O, but this thing is a constant, so I don't really care about it. Okay, and plus log Q times K omega. Now, when you try to put things into this inequality, you realize that, this thing, it's exactly like the magnetic field term for the Ising model. It will appear here and there exactly in the same manner as here and there. Okay? The number of open edges in these two configurations is exactly the same as the number of edges in these two configurations. Okay, you can just check. For every edge, it can be opened either 0 times, once, or twice. And if it's 0, 1, or 2 here, it will be the same value here. So really, the only thing you have to prove, if you want to prove FKG, is that K of omega plus K of omega prime is smaller than K of the minimum plus K of the maximum. Okay, and here I'm using that log Q is positive here. Okay, so to prove this, I just need to prove that. And in fact, what I'm doing here clearly indicates that when Q is smaller than 1, then this is not true, so FKG is actually has much less chances to be true. Okay, we have not seen this as a necessary condition, but I can tell you that when Q is smaller than 1, you have no FKG inequality, so the model becomes really a bit different. Okay, so why is this true? Well, this thing is the same as saying that K of omega, okay, let me write it, minus K is smaller than K of omega prime. Yes. Okay, so this is the same thing as this. And okay, now the idea is, okay, here you have one configuration. And here you have, okay, so here, okay, here you have a configuration, A. Okay, and here you have a connection which is A. Okay, so no. Here you have a connection. Let me use sensible notation. So here you have a configuration omega bar. And here you have a configuration which is omega bar union something. Okay, so disjunct union, actually. Okay, which I call, say, V. Okay, and here what you have is a configuration omega bar prime, which is larger than omega bar. And here you have omega bar prime union exactly the same thing. Okay, you're adding, to go from here to there and to go from here to there, you're adding the same edges. They are exactly the edges that are in omega prime and that are not in omega. Okay, so the important thing here is that you have that omega bar. Yeah, let me call just omega, because this is really omega. So what's important here is that omega bar, it is smaller than omega. Okay, and what you want to say here is that now, when you're deleting edges from a when you're adding edges to a configuration, basically, okay. So what you want to say is that, I mean, here you're adding the same set of edges. You want to say that you kill less connected components when you have more edges at the beginning. Okay, and this is something, okay, you can check it edge by edge, and this is basically what is done in Werner's lecture note. Okay, so basically what you want to say, okay, so you start from this configuration, omega and omega bar, and you just you start from this configuration, and you start adding one edge to both of them. Okay, so what you're saying is that if you're killing a component here, okay, you will okay. If you're killing a component here, then you have to kill a component there. Okay. If you kill a component here, it means that the two things that you're linking between your edges, they were not linked before. Okay? And if they are not linked here, they are not linked here because these things they have less edges. Okay? And then you can iterate and prove that this is true. Okay, just so that Okay, so you have another model that satisfies FKG. So just to say that FKG is something quite general. So now you can prove that the P1 has a limit, and yes, now we would like to say something about this limit and how this limit is related to the infinite volume Gibbs states for the Ising model. Okay, so let me try to say something about this. Okay, and from now on I will be very unwavering. So let's E lambda PQ. E1 PQ to be the limit when lambda goes to ZD of E PQ, E1 lambda PQ. Okay, so one observation is that if you look at this thing here, the magnetization at the origin, okay, this thing is equal to, well, if we use our Ising pots connection, Ising FK collection, what we obtain is that actually, I mean, if there are two cases, either 0 is connected to the boundary for the FK percolation, or 0 is not connected to the boundary. If 0 is not connected to the boundary, basically you're sampling its spin at random, and therefore its average is 0. If 0 is connected to the boundary, then the spin is fixed to be plus. So this thing is exactly the probability that 0 is connected to the boundary of lambda for the percolation. Okay? And actually, I mean, because all the edges outside the box are 1, okay, you can say this is the same. This is actually the probability that 0 is connected to infinity. Okay, so in particular, what you have is that m star of beta. Okay, this is not a local function, but this does not really matter. It can be approximated by local functions, so I'm not cheating very much. It's equal to the probability that 0 is connected to infinity under the infinite volume FK percolation. Okay, so basically you have two cases. Either P1 percolates, and in which case you have uniqueness of Gibbs states for the Ising model. No, either P1 doesn't want percolate, and in this case you have uniqueness for the of the Gibbs states for the Ising model, or P1 percolates, and you have plurality of Gibbs states for the Ising. Well, somehow you have something similar for Potts model, for Potts model, okay? But the difference is that for Potts model you have, okay, you don't really have this does not really imply uniqueness directly, okay? Because when to show that, okay, so for Potts model, okay, you get that the mu beta mu lambda beta okay k okay mu okay 1 of sigma 0 is equal to I, converge when lambda goes to ZD, to 1 over Q if P1, PQ does not percolate. Okay, and it converges to, well, something which is biased towards 1. So it's, yeah, it's, okay. Theta PQ indicator I equal 1 minus 1 minus theta. Okay, well, theta PQ is a percolation probability over Q. Okay, so this ensures multiplicity of Gibbs states. Here you have to work more to prove uniqueness of Gibbs states, because if you remember, we used really the order on spins in order to show that magnetization at zero magnetization implied uniqueness of Gibbs states. Okay, so here you know that if you have several Gibbs states, I mean that the Gibbs states are symmetric in a sense. But, this is all you get. Okay, but now what I want to emphasize is that also having the FK percolation perspective allows yourself to ask for other kind of questions. Because, okay, so far we have just looked at the boundary condition 1, but you can also look at things with boundary condition 0. And the fact is that what you obtain is that, well, you know that P0 lambda PQ of F is smaller than P1 lambda PQ of F for F local and increasing. And I mean, basically, what we have said for P1 is also valid for P0, except that the monotonicity is in the other direction. So therefore, you have another limit for P0. I mean, like you have P1, which is P1 lambda, which is decreasing, P0 lambda, which is increasing. They both converge to a limit, and you can ask yourself, well, do we have P1 PQ equal to P0 PQ? Okay, so there is a cheap answer to this, which is actually, yeah, you have this kind of convexity argument that we had for Ising model that tells you that, well, this is true actually for every value of P except maybe countably many values. Okay, I mean, basically Q plays the role of beta and P plays the role of H here. And like if you look at the free energy of the model as a function of log P over 1 minus P, this is a convex function, and therefore it has to be differential almost everywhere. And differentiability, I mean, the derivative of the free energy, it really corresponds to the density of edges for this measure. Therefore, if they have the same density of edges, the two things must be equal for the same argument as for the Ising model. But basically, this does not tell you what might happen on very particular points. And in particular, here the crucial question might be what happens for the critical value of P. And what does the question mean in terms of Ising model? It means, okay. If you look at the Ising model with free boundary condition, then basically the existence of P0 tells you that there is a limiting Gibbs state. Okay? To know whether these Gibbs states, okay, so if you have this inequality, it tells you that the Gibbs state is just obtained by taking plus boundary condition with probability 1/2 and plus minus boundary condition with probability minus 1/2. Okay, because basically, yeah, this is, how do I justify this? Yes, so, okay. Okay, so yes, so I mean, this thing in the limit, it gives you the free boundary Ising model, okay? And the way you do this is just you sample this measure, and then you sample a spin at random for each connected component. Okay? if this measure corresponds to this measure, then this means that here what you're doing here is you're sampling at random, but there is one of the components which might be, I mean, in the case where you percolate, one of the components corresponds to the giant component that was connected to the boundary. Okay? And therefore, I mean, choosing a spin at random for that component, it really corresponds to taking plus boundary condition with probability 1/2, taking minus boundary condition. So for the Ising model, it's actually true that free boundary is always 1/2 of plus boundary plus 1/2 of minus boundary condition at every temperature. For Potts model, actually, this is not true. So, like for Potts model, what we have is that P1 equal P0 for all P which is different from PC of Q, and PC of Q is the percolation threshold for this model. Okay, so like it's not obvious from here that the percolation threshold is the same for P0 and P1, but this is a. And at P equal PC, what we have is that P1 is equal to P0 for Q smaller or equal to 4, and P1 is strictly larger, well, is not equal to P0 for Q larger than 4. Okay, so this means that, yeah, basically if you take Potts model with more than 4 colors, you have this really weird thing that happens at criticality, which is that you have lots of Gibbs states. You have Gibbs states in which you see one color dominating, and you have a Gibbs states where things are really symmetric with respect to all colors. Okay, so the Gibbs states with the free boundary is actually something which is where all colors play the symmetric role, and you don't see an ocean of one color. Okay, which is really something. Okay, which is. I don't. It's kind of difficult to imagine how this thing occurs when you think about the Ising model, but it turned out that. Yeah, when you don't have this correlation inequalities between spins, lots of things can happen. Okay, so maybe a last comment, and then I should stop because it seems that I'm making less and less sense as I'm advancing. But one question you can ask is about what is the critical point for this percolation model, and I mean this thing is kind of equivalent to asking what's the critical temperature for the Potts model when Q is an integer. So maybe a remark before this is that this representation, it provides you for, it already gives you different proofs for studying the low temperature and high temperature regime for the Ising model. Okay, because, I mean, for instance, if you want to show that P1 doesn't percolate for small p. So this is showing that m star of beta is equal to 0 for small beta. Yeah. Then you can just compare to standard percolation. Okay, in FK percolation, you have less edges than standard percolation. So you kind of have this result for free. In the other direction, it's more complicated because the comparison doesn't go in the right direction, but yeah, you might try to adapt this, the counting argument you had, taking into account the fact that, okay, the term where connected components show up. And I think you can do this basically, that if P is sufficiently large, yeah, I guess you can do this thing with this duality argument. But now if you want to identify exactly the critical point, Well, a good intuition you might have is to try to look at so to identify PC of Q, you might want to look at the point at which the model is self-dual. Okay, so when you're looking at FK percolation, you can always look at the dual process, which is still a percolation process. The dual process lives on the dual graph. Of course, because you've taken all edges, well, if you take one boundary condition, okay, the dual process will have 0 boundary condition because all the corresponding dual edges will be closed. Yeah, the thing is that there is a special value of P for which basically, well, if you want the dual process, so P star lambda P Q1 is equal to P 0 lambda star. Okay, so what you have is this. Okay, you can always find a parameter P star such that this is true, and you have P equal to P star for P equal to, I think it's this thing. Let's see, what we had is, yeah, it's this one. Yeah, it has to be larger than, it's 1/2 for P equal 1, and it has to be larger than 1/2 for, it's 1/2 for Q is equal to 1, and it has to be larger than 1 for, okay, so, okay, so this is just an observation that follows from a relatively simple computation, but this kind of strongly indicates that the model should be critical exactly for this value of P. Yeah, this is something that took 50 years to be proved. Now there are several proofs of this. In particular, for the case Q equals to 2, this gives you also a proof for the critical value of beta for the Ising model. Okay, so I think I will stop here. So thank you very much for attending the class. Yes, if you have any questions, well, please ask now. Yes, and this is it.